Students, welcome for the fifth session of lecture on elementary particles. Now let us summarize the classification of elementary particles from the above diagram. Elementary particles are broadly classified into bosons and fermions. Bosons are again bifurcated into two categories: massless bosons and mesons. Under massless bosons, you have photons and gravitons. You know about photons and also gravitons, which we have discussed in the earlier classes. Mesons are of three types: pi mesons, k mesons, and eta mesons. Eta mesons are eta 0 and its antiparticle is eta 0 complement. Pi mesons are of three types: pi plus, pi 0, pi minus. Similarly, K mesons are of four types: K plus, K minus, K0, and its antiparticle K0 complement. Fermions are of two types: leptons and baryons. Fermions, they obey Fermi-Dirac statistics. Fermions are of two types: leptons and baryons. Leptons are the following types: E minus electron, E plus positron, mu minus, mu plus, nu E, nu E complement, nu mu complement. Baryons are nucleons and hyperons. Nucleons are protons, antiproton, neutron, antineutron. And hyperons are of following types: lambda particle, sigma particle, xi particles, and omega particles. Sigma particles are of three types: sigma plus, sigma minus, sigma 0. Even xi particles are xi 0, xi plus, and xi minus. This is a classification of elementary particles. And this is the table showing some important rest mass and mean life, spin, antiparticle for certain particles, elementary particles. You can learn this table in detail. I will explain one: massless particle graviton, symbol is G, rest mass 0, charge 0, mean life 0, spin 2, antiparticle G minus. Similarly, photon denoted by nu, gamma symbol, rest mass 0, charge 0, it is highly stable, and spin is +1, antiparticle is gamma minus. Similarly, you study this table completely on your own. It is given even in the textbook for all the particles, elementary particles. Learn this table. Even for hyperons, sigma, psi, cascade, omega. Study and remember some important properties. Now, comparison of four interactions. Already we have discussed all the four interactions in the earlier classes: gravitation interaction, electromagnetic interaction, strong interaction, and weak interaction. The relative magnitude: gravitational 10 power minus 39, electromagnetic 10 power minus 3, strong interaction 1. That means if we compare strong interaction and gravitational interaction, the ratio is 1:10 power minus 39. Similarly, strong interaction to weak interaction, 1:10 power minus 14. That's how you should compare the relative magnitude. And then range is given: gravitational infinity, electromagnetic infinity. Strong interaction is within Fermi, 10 power minus 15 meter, Weak interactions will be within 10 power minus 17 meter. Carrier particles, gravitons or gravitational interactions involves gravitons. Electromagnetic interactions involves photons. Strong interactions involves kaons and pions. Weak interactions involves intermediate bosons. Particles affected, it is given the table, and even characteristic time in second is given. And even conservation laws and symmetry already we have discussed, and the notes, handwritten notes, as well as this printed version is given as your study material. Please go through in detail and try to answer all the questions given at the end of the chapter. Even conservation laws for strong and electromagnetic interactions we have already discussed, and here you have detailed one important points you can note down. And conservation laws related to symmetry, conservation of parity. Parity is an important property in a quantum mechanical description of a physical system. In most cases, it relates to the symmetry of wave function representing a system of fundamental particles. So let's learn about parity, how even parity, odd parity, they are conserved in all nuclear reactions with examples. In attempting to understand some puzzles in the decay of subatomic particles called K-mesons, the Chinese-born physicist Sung Do Lee and Chen Ning Yong proposed in 1956 that parity is not always conserved. Lee and Young showed that there was no existence that parity conservation applies to weak interactions. The fundamental laws governing the weak force should not be indifferent to mirror reflection, and therefore particles interactions that occur by means of weak force should show some measure of built-in right or left-handedness that might be experimentally detectable. In 1957, a team led by Chinese physicists announced conclusive experimental proof, and the electrons ejected along with antineutrinos from unstable cobalt nuclei in the process of beta decay. A weak interaction or predominantly left handed, that is to say, the spin rotation of the electron is that of a left handed screw. Nevertheless, it is believed on strong theoretical grounds, that is, CPT theorem, that when the operation of parity reversal P is joined with two others called charge configuration C and time reversal T, the the combined operation does leave the fundamental laws unchanged. So all these some important points you can learn. And here the example is shown how proton is formed. This is only a review on what we have discussed under quarks. Two up quark and one down quark combined with each other becomes a proton. And here the figure, two anti-up quarks and anti-down quark gives rise to an antiproton. Similarly, you can think of two down quark and one up quark will produce a neutron. Similarly, two anti-down quark and one anti-up quark combine to form antineutrino. So this completes the lesson, elementary particles, and little bit of numericals I will work out, and the same will be shared in our WhatsApp group. Please go through the content of both the chapters, dielectrics and elementary particles, and thus the portions for the sixth sem is over. Only numerical problems will be shared on WhatsApp group, and any doubts, any clarification, if you want, you can discuss over the phone or you can discuss in WhatsApp group. Thank you. Wish you all the best of luck.